The third class of reaction that we're going to look at are a type of reaction called oxidation-reduction reactions. And this is by far the most complex of the three reactions that we'll be looking at. So oxidation-reduction reactions are often described as being redox reactions, which is just a contraction of these two words. So what is happening in redox reactions? Well, in redox reactions, electrons are being transferred from one reactant to another. So we saw in acid-base reactions, say an acid being dissolved in water, that what was being transferred was one or more protons. We also saw that in a precipitation reaction, that what was being not transferred but exchanged were ions. In a redox reaction, what is happening is that electrons are being transferred from one reactant to another. So it's a little bit different. So the third class of reaction that we're going to be looking at is a class of reactions known as oxidation-reduction reactions. So previously we were looking at acid-base reactions, and in an acid-base reaction what's happening is that protons are being transferred from the acid to the base. We also looked at precipitation reactions, and what's happening in a precipitation reaction is we have two ionic compounds and there is an exchange of ions and we form two new ionic compounds. In an oxidation-reduction reaction, what's going to happen is we're not going to be transferring protons, we're not going to be exchanging ions. What we're going to be doing is we're going to be moving electrons from one reactant to another. And so we'll have two reactants, and they'll be reacting to form a product, or maybe more than one product, and how that product is going to form is by the movement of one or more electrons from one reactant to the other. So it's quite interesting. So these oxidation-reduction reactions are often referred to as redox reactions, which is just a contraction of those two words. And as I was explaining on the title slide, in a redox reaction, electrons are moved from one reactant to another. So one reactant will lose electrons, that is referred to as oxidation, and the other reactant will gain electrons, and that's referred to as reduction. So there are two processes occurring simultaneously, oxidation and reduction, and that's why these guys are called oxidation-reduction reactions, right? Now you can remember what each term refers to using this little memory aid here, and that is oil rig, which stands for oxidation is loss of electrons and reduction is gain. So you put that together and you get oil rig. So a good example of a redox reaction is the combustion of magnesium in the presence of oxygen. Now we can be pretty sort of like, confident in identifying how electrons are going to move here, because magnesium is a metal, and what do metals like to do? They like to lose electrons. And oxygen is a non-metal, and what do non-metals like to do? They like to gain electrons. So when it's two elements, we often can kind of guess what way the electrons are going to move. They're going to move from the metal to the non-metal, right? That's the way that electrons are going to move. And in this case, the number of electrons it's moving is 2 electrons. So we can separate this reaction into two what we call half reactions. And one of these half reactions or half equations will describe the oxidation process, the loss of electrons, and the other one will describe the reduction process, or the gain of electrons. So what's happening is the magnesium is undergoing oxidation. It's losing electrons. It loses 2 electrons because magnesium is in group 2A. And then the oxygen molecule undergoes reduction to form oxide anion, and it forms a 2- anion because oxygen is in group 6A. So we introduced the concept of a half equation or a half reaction, describing each of these 2 processes. Okay, here's where it gets a little weird. We can give our reactants a title. We can say what is happening to them. We can say the magnesium is oxidized, or we can say the oxygen is reduced. But we can also label what the reactant is in terms of how it's behaving. And in particular, what we can say for this case is that magnesium is the reducing agent. And what that means is it causes the other reactant to be reduced, to cause the other reactant to gain electrons, right? And we can also say that oxygen, O2, is the oxidizing agent. It causes the magnesium to become oxidized. It takes 2 electrons from the magnesium. Now, this is a little bit confusing because what is happening to the magnesium is that it is becoming oxidized, but that means that the magnesium is the reducing agent. And what is happening to the O2 is that it is being reduced. But what that means is that the O2 is the oxidizing agent. So the verb and the noun are kind of, different things, right? Okay, one is describing a process that is happening, the other is describing the identity of the reactant. So you have to be really careful with the grammar. So here's a example of a very famous redox reaction. It's called the thermite reaction. It's the reaction between solid aluminum and solid iron 3 oxide. And it's unusual because it's a reaction between 2 solids. And the product of the reaction is liquid iron at around about 3000 degrees Celsius and solid aluminum oxide. So it's a pretty exciting reaction because it gets so darn hot. Now, what has happened here is that electrons in this case have moved from the aluminum to the Fe2O3. So that's the direction in which electrons are moving. So the question becomes how do we know this? It's kind of non-obvious. In the other case that we had a metal and a non-metal, and it was really obvious that the electrons would move from the metal to the non-metal. What about this case where we've got a metal reacting with an ionic compound? Why would we know that the electrons are going to move from the metal to the ionic compound? So that's one of the difficulties that we're going to kind of come across, is how can we recognize what direction the electrons are going to move in? So the first step in kind of being able to answer this question is to recognize that electron loss and electron gain occur simultaneously. They can't occur without the other one occurring, right? So you can't gain something unless somebody loses something, right? So, it's kind of like, if you beat your little brother up and steal their money, you can't gain money without them losing money, right? That's what happens. So that's how we end up with these kind of names of reducing agent and oxidizing agent. The reactant that is oxidized, that means it loses electrons, causes the other reactant to gain electrons. All right? So it basically pushes electrons into the other one. So for that reason, it's referred to as the reducing agent. Now, the reactant that is reduced, that means that it gains electrons, is called the oxidizing agent because it forces the other thing to get oxidized or to lose electrons, right? So these names kind of do make sense, but again, it's that kind of like difference between the noun and the verb, right? One is something that it is, the other is something that it does. So it's a little confusing. So recognizing that there's always going to be something that loses and something that gains, and that those processes occur simultaneously, what we want to be able to try and do is, figure out how these electrons are going to move. And to help us with that, we have a system of numbers which are called oxidation numbers. And that's going to be the key to identifying what way the electrons are moving. So in this system, which we won't explain exactly where it comes from until later on in the general chemistry sequence, we're just going to explain how you can use it at this point. In this system, what you do is every single atom, whether it's in a polyatomic ion, whether it's by itself in an element, whether it's in a compound, is assigned a number, and that number is called the oxidation number. And how we're going to assign these oxidation numbers to these individual atoms, molecules, ion, or individual atoms that are within molecules or ions, or just within the element itself, is by following a series of rules. Now, there are 4 of these rules, and sort of like one of those rules has kind of 3 or 4 parts to it. So you'll see like other people kind of have the rules structured in a different manner, but I'm trying to follow what's given in your book. If you see another list of these rules that's slightly different, I'm sure that that list will work just fine. So the first rule is pretty simple. The oxidation number of any uncombined element, so O2, N2, Br2, if it's a a diatomic element, P4, S8, all of the other ones are just individual atoms, aren't they? Monatomic elements. The oxidation number of any uncombined element is 0. Pretty simple. All you got to remember is that some of our elements, 7 of them are diatomic, and then we have P4 and S8 are not monatomic elements, and everything else is monatomic, right? The second rule is pretty easy as well. If we have a monatomic ion, or a simple ion, as I've called it here, monatomic ion, then the charge on the ion is just equal to the oxidation number. So if you have an Mg2 plus ion, then its oxidation number is just +2. If you have a O2 minus ion, then its oxidation number is -2, and so forth. So real easy. Now, a little something that can help you out here is that metals are almost always present in compounds as ions. So if you see a metal in the formula, NaCl, you know that that's going to be an ion. Sodium always forms a +1, so oxidation number is going to be equal to +1. Now, I'll show you the convention that most people follow is to put the sign of the oxidation number and then a number indicating the magnitude. When it comes to charge, people tend to write it the other way around. Not everybody, but that's the convention that most people follow. Okay, so then this is the rule that I said that has a kind of a couple of parts to it, and these are rules that apply to non-metal atoms that are specific to a particular element. So the first one is a rule that's particular to hydrogen, and it says the oxidation number of hydrogen in compounds is most commonly +1, right? The exception is when hydrogen is combined with a metal, so just one metal by itself. In that case, the oxidation number of hydrogen is -1. So these kinds of compounds are referred to as metal hydrides, and because the H- anion is called the hydride ion. Okay. The next part of this rule applies to oxygen in compounds, and in most compounds, oxygen has an oxidation number of -2. But there is a couple of exceptions, and the exceptions are peroxides, the most famous being H2O2, where oxygen has an oxidation number of -1, and when they're combined with fluorine, when oxygen is combined with fluorine, then we're going to have to use other rules to figure out the oxidation number of oxygen. So if I had the water molecule, I would recognize that this is not hydrogen peroxide, this is not in the presence of fluorine, so oxygen is going to have the oxidation number of -2. Now, it says in Rule 3a that the oxidation number of hydrogen compounds is normally +1 unless there's a metal present, so I would know that hydrogen here is +1. So I would have assigned oxidation numbers to every atom that is present in the substance water. Okay, the third rule concerns the oxidation numbers of the halogens. And this one is really simple. The first part of this rule is really simple. It says that in compounds containing fluorine, the oxidation number of fluorine is always, without exception, -1. So whenever you see fluorine in a compound, you can just automatically go ahead and give it the oxidation number of -1. And then the second part of this rule is concerning the other halogens. And it's pretty simple. It says unless combined with oxygen, fluorine, chlorine, and bromine, and I guess you could put in here iodine, have an oxidation number of -1. So that's it. Unless combined with oxygen or fluorine, chlorine and bromine, and also iodine have an oxidation number of -1. So yeah, that's pretty simple. So here we have fluorine, so we know that the fluorine is automatically -1. Here we have chlorine. It's not combined with fluorine or oxygen, so the chlorine is -1. Now in this case, we have the perchlorate anion, and we can see that the oxidation number of the chlorine is not -1, and we'll have to learn how to assign that soon. Okay, our final rule, and I'm going to give this in 2 parts, is pretty simple. It says, and this is arguably the most useful of all of the rules. Okay, it says the sum of oxidation numbers of all atoms in a compound or ion is equal to the overall charge. So for compounds, the overall charge is 0, and then for a polyatomic ion, you know, the charge is going to be written up there in the top right corner, isn't it? So if we have this compound here, magnesium sulfate, we know that the sum of all of the oxidation numbers has to add up to 0 because this is a compound. Now magnesium is a metal, and metals are always present as ions. And magnesium is in group 2A, so it always forms a +2 ion. And for ions, the charge is equal to the oxidation number. So magnesium has an oxidation number of +2. Now, the oxygen in compounds normally has an oxidation number of -2 unless it's in the presence of fluorine or it is hydrogen peroxide. Now this compound is not hydrogen peroxide and there's no fluorine present, so the oxidation number of the oxygen is -2. But now we're stuck. The sulfur, we have no special rule for the sulfur. But what we do know according to rule 4 is that all of the oxidation numbers together have to add up to 0 because this is a compound and the overall charge on a compound is 0. So let's just do that, right? So 2 is the oxidation number for the magnesium, and then X is the oxidation number for the sulfur. And then we have 4 oxygens and they each have an oxidation number of -2. And when you add all of that together, it's got to equal 0. So let's do the math here. This is going to end up being X minus 6 equals 0. So that means that X equals plus 6. So by using rule 4, I'm able to get the oxidation number of the sulfur, which I don't have a specific rule for. So just revising that, magnesium is present as an ion because it's a metal. Magnesium is in group 2A, so the charge on its ion is +2. That means that the oxidation number of magnesium is +2. Oxygen always has an oxidation number of -2 unless it's with fluorine or in the compound hydrogen peroxide. None of those two special cases apply in this situation, so the oxygen has an oxidation number of -2. To solve for the oxidation number of the sulfur, which is unknown, I use rule 4 that says for a compound, the oxidation numbers have to sum to the overall charge. And for a compound, the overall charge is always 0. So that means that I've got to add together the oxidation number of the magnesium to the oxidation number of the sulfur to 4 times the oxidation number of the oxygen. And all of those added together will equal 0. And then I can solve for X, which in this case, which indicates the oxidation number on the sulfur. So rule 4 is really handy. Like I said, it's often your most useful rule. You need it really when you don't have a specific rule for your particular atom that you're looking at. Okay, so the next thing we're going to do is look at the oxidation numbers in the polyatomic ion bicarbonate. So we've got hydrogen, and we have a rule for that. The oxidation number of hydrogen is +1 unless the hydrogen is in a compound with just a metal hydride. It's not, so the oxidation number of hydrogen is +1. We don't have a special rule for the carbon, so we're going to have to come back to that and apply rule 4, but we do have a rule for the oxygen. The oxidation number of oxygen is always -2 unless we have hydrogen peroxide as our compound or fluorine is present. None of those special cases are relevant here, so the oxidation number of the oxygen is -2. Now, to figure out the oxidation number of the carbon, which we don't have a special rule for, we're going to apply rule 4 that says when I add together all of the oxidation numbers for this polyatomic ion, it's going to equal the overall charge. So I've got 1 hydrogen, which is +1. I don't have a rule for the carbon, so that's just going to be X. And then I've got 3 oxygens, and they're -2. And the whole thing has to add up to the charge, which is, in this case, it's not a neutral compound, it's a polyatomic ion, it's going to be -1. So if I put all of that together, this ends up being X minus 5 equals -1. So X equals +4. There we go. All right. Make that look a little more like a 1 and not a 7. There we go. So rule 4 is really, really helpful. So I've posted some worksheets, and you can practice assigning oxidation numbers to atoms in compounds. Okay, so the reason that we were trying to do this is so that we could identify how electrons were moving in a chemical reaction. So the key thing is what we have to do is define oxidation and reduction in terms of changes in oxidation number. And what we're going to say now is that oxidation is indicated by an increase in oxidation number, and reduction is indicated by a decrease in oxidation number. So in this way, we can see which reactant has atoms that are increasing the oxidation number, that is the thing that is getting oxidized, and which reactant has atoms that are decreasing their oxidation number, and that's the reactant that is becoming reduced. So going back to our original example of magnesium reacting with molecular oxygen, magnesium in our first half reaction here is in the elemental form. It has oxidation number 0. Magnesium on the product side is in the ionic form, and it has oxidation number +2. For our reduction half equation, the molecular oxygen is in its elemental form, so it has oxidation number 0, and then on the product side, the oxygen is present as 2- anions, so they have oxidation number -2. So what we can see is there was a decrease in oxidation number for the oxygen, and there was an increase in oxidation number for the magnesium. So that means that the magnesium underwent oxidation or is our reducing agent, and the oxygen underwent reduction or is our oxidizing agent. So, that's how it works, right? So if you want to identify what is undergoing oxidation, what is undergoing reduction, what is the reducing agent, what is the oxidizing agent, you need to assign oxidation numbers and think about these definitions. Okay, and it's easy to get confused. So you might want to practice trying to do this, by using those worksheets that I've posted. So you'll have to be able to identify, given a chemical equation, what species is being reduced, what species is being oxidized, and then also be able to identify what is the reducing agent, what is the oxidizing agent. And how you're going to do this is by giving everything oxidation numbers and seeing what increases and what reduces its oxidation number. So here's a combustion reaction. This is methane reacting with oxygen to form carbon dioxide and water. Methane is an example of a hydrocarbon. It's the simplest hydrocarbon. And what we see here is that the carbon increases its oxidation number from -4 in the methane to +4 in the carbon dioxide. So we know that the methane is being oxidized. Notice that the convention is that the whole reactant, the compound that contains the atom that is being oxidized, is identified as the species that is being oxidized. You don't say carbon is oxidized, because it actually doesn't make any sense, because there is no carbon present. There's only carbon in methane. So you could say the carbon in the methane is oxidized, but that's too much. We just tend to say the methane is oxidized. Okay, and then now if we look at this, we'll see that the O2 here, the molecular oxygen, its oxidation number changes from 0, because it's in the elemental form, down to -2. So the O2 undergoes reduction. The O2 is reduced, or we can also say that the O2 is the oxidizing agent. Got to be a little bit careful with the language there. Again, we don't say that O is reduced. We could say oxygen in O2 is reduced, but that would be weird. The convention is just to say O2 is reduced. So we give the whole species containing the atom that got reduced. Okay, so that's kind of how it works, right? Okay. Now you'll also see here that some atoms are neither oxidized nor reduced. Not everything has to be oxidized or reduced. And in this case, the hydrogen atoms are neither oxidized nor reduced. And that's not uncommon for there to be one or more atoms that are not undergoing changes in their oxidation number. Okay. Again, just reiterating this point, oxidation and reduction occur simultaneously. One can't occur without the other. What does it mean that the methane was oxidized? It means that the methane lost electrons. So electrons moved from the methane to the O2. What does it mean that the O2 was reduced? It means that the O2 gained electrons. And you can see how that works. They are indeed simultaneous processes. The methane causes the O2 to become reduced, so it is described as being the reducing agent. The O2 causes the methane to be oxidized, so it is described as the oxidizing agent. So just being careful with these definitions. One is kind of a name, the other is a process that the reactant is undergoing. All right, so you do need to be able to identify these things. Keep hammering you on this point, and just be very careful in giving these names to these reactants. Something else that you're sometimes asked to comment on is the number of electrons that are being transferred, and it's pretty simple. The number of electrons that is being transferred is just equal to the change in oxidation number. There's really only one thing that you have to keep in mind, that the oxidation number is for one atom, and if you have multiple atoms, you've got to take that into account. So for example, here we see that the change in oxidation number for this one carbon atom is from -4 to +4. So the change in oxidation number is 8, and so that tells us that 8 electrons are being lost. Now, when we look at the O2, right, we have 4 atoms, and each of them is changing by 2. So 4 times 2, so that's telling us that 8 electrons are gained. Right? And a very important quality of redox reactions is that the number of electrons lost always equals the number of electrons gained, right? Because the electrons are just moving from one place to another. So what is really happening in this combustion of methane reaction is that 8 electrons are moving from the methane into the O2 molecules. 8 electrons are being transferred from the reducing agent to the oxidizing agent. So every now and then you'll be asked to comment on how many electrons are being transferred, and how you're going to do that is by looking at 2 things: the number of atoms that are undergoing the change, and then also the size of that change in oxidation number. Okay, sometimes this can kind of get tricky because you'll find that your atoms kind of get like scattered across the products. And then other times it's like a lot easier. So if I look at this one, in this case we've got N2, or we've got nitrogen being oxidized from -2 to +2, and then we've got oxygen being reduced from 0 to -2. We need to figure out how many electrons are being transferred. So we've got 2 nitrogen atoms, and each of them are changing by 2. So that's 2 times 2, that's 4 electrons going to be transferred. Okay, so it's pretty simple. Does it work when we go the other way around? We've got a change of 2 and 2 atoms that are undergoing that change. So 2 times 2, again, 4 electrons being transferred. So you just got to kind of keep an eye on everything and make sure you kind of understand what's going on. All right, so identifying oxidizing agent, identifying reducing agent, identifying what is being oxidized, identifying what is being reduced. It's all based on oxidation number. Also, identifying how many electrons are being transferred can all be achieved by knowing how to assign and use oxidation numbers. So that's kind of the beginning part of the chapter. The second part of the chapter is all concerned with balancing these redox reactions, and it's a doozy. Balancing a redox reaction requires an 8-step process. It's a systematic process, whereas previously when we were balancing reactions, we were just kind of doing it by messing with the coefficients. That isn't going to work necessarily for redox reactions. In fact, most of the time it won't work for redox reactions. So a good example of why you kind of need to be a little bit cautious in balancing redox reactions is this example here of the reaction between silver ions and solid copper. And this is kind of cool. When you take a solution of something like silver nitrate that contains silver ions, and then you put a piece of solid copper in it, and something very interesting happens. The first thing that happens is the copper starts to dissolve and it forms bright blue copper ions, which is really cool. So the solution turns blue. The other thing that happens is solid silver, which is obviously like quite sparkly and nice, starts to rain down as a solid from the solution. So it's pretty cool. You have this thing and it kind of instantly turns blue, the copper starts disappearing, and silver starts falling out of solution. You might be able to find a YouTube video of this. It's kind of fun. Now, if I was to write a balanced equation for this guy, I'm going to react silver ions with solid copper, and that's going to form solid silver and copper 2+ ions. And I might consider, oh, this is all balanced when everything is 1 to 1 to 1 to 1. And, it kind of makes sense, right? We got one silver on the left, one silver on the right. We've got one copper on the left, and we've got one copper on the right. Isn't that balanced? Well, not really, because the total charge on the left is +1, and the total charge on the right is +2. So this means that this side has one less electron. So we can't consider this to be balanced, right? Because, we can't just have like, poof, an electron disappears. That would be disaster if electrons just kind of in the universe were just like randomly disappearing. We wouldn't be able to account for anything. So this reaction is mostly balanced for mass in that the atom types are the same on both sides, but it's not balanced for charge. We've lost an electron. So how do we fix it? Well, you can probably see by inspection how we might fix this. If we put a 2 here and a 2 here, then this would work out, right? Okay. Now, you can see that, and you don't need to do this sort of like lengthy 8-step process that I'm going to go through in this case. And, but this is like baby stuff, right? This is not a typical problem. So to balance the equations for redox reactions, we've got to account for the number of electrons that are transferred, right? We've got to make sure that we don't lose any electrons along the way. So to balance a redox reaction, we're going to use an 8-step process, and I put the 8 in all caps because it's kind of daunting, isn't it? Now the good news is that that's a worst case scenario. Often, and you'll see in this example, multiple of those steps are not used. They're not relevant, okay? So don't freak out too much. You do need to know all of the steps. They're listed in your book. You can kind of just bookmark that page, or you can find another another website that has those 8 steps listed out and bookmark that. But it is an 8-step process. The first step is to break your unbalanced reaction into oxidation and reduction half equations. So we've got 2 things going on here. The copper gets oxidized to copper 2+. That's our oxidation half reaction, and our silver silver ions get reduced to silver solid. Okay, so now we've got 2 half reactions. The next thing that we're going to do is balance all of the atoms within our half equation except hydrogen and oxygen. Okay, so balance each half equation for atoms other than hydrogen and oxygen. And this is what I said in this case, and in many other cases, there's nothing to do. 1 copper on the left, 1 copper on the right, 1 silver on the left, 1 silver on the right. So it's pretty easy. Then what we do is we balance for oxygen by adding water. And again, in this case, nothing to do because there is no oxygen. So we just kind of keep on moving. Our 4th step is to balance for hydrogen with H+. And again, in this case, there's nothing to do. So, there's 3 out of the 8 steps that we're just going to cruise on through. This step you always have to do, number 5. It is balance for charge by adding electrons. And the electrons are always added to the more positive side. So let's have a look here. If I look at my oxidation half reaction, I can see that the total charge on the left is 0 and the total charge on the right is +2. So I have to add 2 electrons to get the right hand side down to 0. If I look at my reduction half equation, I can see that the total charge on the left is +1 and the total charge on the right is 0. So always add electrons to the more positive side, so I have to add 1 electron to the reactant side of the reduction half equation. All right, so what you can see now is that we have electrons on opposite sides of the arrow in each of our 2 half reactions, and that's what we want. We want our reduction half reaction to have electrons on the left, and we want our oxidation half reaction to have electrons on the right. And as long as we've got that, we're okay. Now, you can probably see that there's a little bit of difficulty here. The reduction is consuming 1 electron, but the oxidation is only producing, the oxidation is producing 2 electrons. So the number of electrons that is being lost is not equal to the number of electrons that is being gained. So what we have to do now is to multiply one or both of the half equations by whole numbers so that the electrons lost equals the electrons gained. And what we saw was 2 electrons were being lost, but only 1 electron was being gained. So I need to multiply my reduction, the whole thing, by 2. So you can see that I've done that here. I've multiplied everything by 2. Okay, so now we're good, right? As many electrons are being lost as are being gained. So what I can do now is add these guys together, and I'm going to add them together and I'm going to cancel where possible. And the things that I can cancel are those things that appear on different sides of the arrow. So in step 7, you're going to add the 2 half equations together, cancelling wherever possible. And at the very least, you should be able to cancel out all of the electrons, right? Okay, so in this case, the 2 electrons cancel, but there's nothing else that are on different sides of the arrow. So here's my overall balanced equation. Okay, 1 copper solid reacts with 2 silver ions to give 1 copper 2+ ion and 2 solid silver atoms. When I go through and double check everything, which I totally recommend that you do, I'm going to check copper atoms, they're the same on both sides. I said silver atoms, they're both on the same sides. And what I do that's different for most of the time when I'm balancing is I'm going to check the charge is the same on both sides. So if I do that, it's all good. Now there is an 8th step, but that only applies in basic conditions. So unless the problem tells you that the conditions are basic, that is that the hydroxide ion is present, we aren't going to be doing step number 8, and we can stop after step number 7. Okay, so this is it here. So it says if in basic conditions, we're going to add 1 hydroxide to each side of the equation for every H+ that is present after step 7. Then we're going to combine H+ and OH- to form water and cancel out things wherever possible. So this is like, holy cow, this is a big step. But the thing is, you don't have to worry about it unless it specifically tells you that you're in basic conditions. So in this case, the problem didn't ask for that, so there is nothing to do. All right, so let's have a look at another one. It says, balance the following redox reaction. So the first thing to notice is it's not base. Woohoo! So no step 8, okay? So step 1 was break it into 2 half equations. One describing the oxidation of tin 2+ to tin 4+, and then the other is going to be describing the reduction of I2 to I-. Okay, done. Pretty simple. Just break it into 2 half reactions, 1 for each reactant. Now what are we going to do? Balance atoms that are not oxygen or hydrogen. So 1 tin, 1 tin. It's already done. 2 iodines, and I had to add in the 2 there to get the iodines to balance. So now that's balanced. What do we do now? Balance for oxygen by adding water. It's not needed, right? And then we've got to balance for hydrogen by adding H+. It's not needed, okay? So the 2 steps in the middle there, balance for oxygen and balance for hydrogen, we didn't have to do those, right? So balance for oxygen by adding water, balance for hydrogen by adding H+, not needed. So we're going to skip to balance for charge by adding electrons to the more positive side. The top one here, the oxidation half reaction, 2 plus on the left, total charge of 4 plus on the right, so that tells us electrons are going to go on the right hand side. We've got to add in 2 electrons, so plus 4 plus 2 electrons is going to give me plus 2. I've got the same charge on both sides. In my other reaction, I had 0 on the left, and then a 2 times minus 1, I had minus 2 charge on the right. So the more positive side is the left-hand side. I need to get 0 down to minus 2, so I have to add in 2 electrons. So each electron is minus 1, so minus 2 plus 0, and it's going to give me minus 2. I've got the same on both sides. Okay, so once I've balanced for charge, what is next? Multiply one or both of my half reactions by a whole number so that the number of electrons lost equals the number of electrons gained. Well, guess what? I've already got there, so there's nothing to do, right? So I don't need to multiply one or both of these reactions by a whole number because I'm already there. So like I said, many of these steps you don't need to do. Okay, so once I've realized that, I'm just ready to add these guys together, right? So I'm adding them together, and I'm going to cancel out where I have the same thing on opposite sides of the arrow. And so in this case, that's just going to be the electrons. So what have we got? Tin 2 plus I2 gives tin 4 plus and 2 I minuses. So when I double check everything, I've got 1 tin on the left, 1 tin on the right. So they balance. I've got 2 iodines on the left and I've got 2 iodines on the right, so they balance. And then I'm going to look at my total charge. I've got a total charge of 2 plus on the left, and then 4 plus 2 minus gives me a total charge of 2 plus on the right. So it all balances, right? Everything is looking good. I guess what we haven't done now, and it's not really a big secret, is we haven't balanced any equations where we've got oxygen and hydrogen, or any equations where we're under the basic conditions. So we need to do a couple more examples. But first I think I'm going to have to stop and feed my dog because you can hear him squealing in the background. He's getting a little impatient. So if a redox reaction is occurring in the presence of acid, our process tends to be a little more complex and we have to start using a few more of our other rules. Not quite as complex as if it is under basic conditions. So here's what you'll typically be given, what's called a skeleton reaction or an unbalanced reaction. And it specifies in this case that it's under acidic conditions, which is really just another way of saying not basic, but it's also a way of saying that you can add hydrogen ions if you need to, or you could add water if you need to, that you have as many of those things as you like to available to add. So we're just going to have a quick look at it and identify what is getting oxidized and what is getting reduced. And so it's Fe2 plus MnO4 minus, which is the permanganate anion, getting converted to Fe3 plus and Mn2 plus. And we can see it's not balanced because there's no oxygen atoms at all on the right hand side. So the Fe2 plus is getting oxidized from the plus 2 oxidation state to the plus 3 oxidation state. Now it takes a little bit of work to get here, but the manganese in this polyatomic ion here has an oxidation number of plus 7, very common oxidation number for manganese. And then on the right hand side, it's just as the monatomic cation, so it has an oxidation number of plus 2. So it's getting reduced by 5 electrons. Okay, so now what we're going to do is break it into our 2 half reactions, one for the Fe2 plus, one for the MnO4 minus. So we're writing out the 2 half equations. And then our next step is to balance for atoms that are not oxygen or hydrogen. And it turns out that there's nothing to do here because we've got 1 ion producing one iron. We've got one manganese producing one manganese. So we're going to balance for everything other than oxygens and hydrogens, and there's like nothing to do there. The next thing is to balance for oxygens by using water. And while there's nothing to do for the oxidation half reaction, we're going to have to add 4 waters here, right? Aren't we? We're going to have to deal with the reduction half reaction there. So we're going to balance for oxygen by adding H2O, and how we're going to do that is by adding in 4 waters. Now we can add in as much water as we want, right? Because this is all in aqueous solution, so there's an abundance of water around the place. Okay, so what's next? The next thing is that we're going to balance for hydrogen by adding H+. And again, we can do that because it's acidic conditions, right? So we have an abundance of H+ present in this solution. So what have I got to do? Well, the top one doesn't have any H+ there, but any hydrogens there, but this one here has got 8. 4 times 2, there's 8 hydrogens on the right-hand side there, so I'm going to have to add 8 hydrogens to the left. So here we go, we've balanced for hydrogen by adding H+. So there's only one more step before we have to combine these guys, and that is to add electrons so that the charge balances, and we're going to add the electrons to the more positive side. So we need to identify the total charge on either side of our half reaction. So the total charge here is +2, and the total charge over here is +3. So we're going to be adding electrons there. Now, you guessed it, we have to add them to the other side for the reduction, don't we? So let's have a look at what the total charge is. The total charge on this side is +2, because we just got that guy. On the left-hand side of this reaction is a little more difficult. We've got 8+ here, and then we've got 1- there, so the total charge is +7. All right, so we're going to be adding electrons to the more positive side, so you're going to be adding some electrons over on the reduction side, over on the left-hand side of the reduction half reaction. So what do we got to do? We've got to add 1 electron, all right? 1- plus 3+ gives 2+. Okay, and then we've got to add 5 electrons here to get the charge to balance. 5- plus 8+ gives me 3+, plus 1- gives me 2+. And then over here, we've just got the 2+. Okay, so everything is looking pretty good. The only difficulty that we have now is that the number of electrons lost doesn't equal the number of electrons gained. So if we were to add these two half equations together now, not all of the electrons would cancel. So what we've got to do is multiply one or both of our half equations by a whole number so that the number of electrons lost equals the number of electrons gained. And you probably can see what needs to happen. I'm going to have to multiply my top reaction here by 5. So I multiply everything in the top line by 5, and then I've made certain that my number of electrons that is being lost in my oxidation equals the number of electrons that's being gained in my reduction. And then now I can go ahead and add together, cancelling where possible. And in this case, it looks like the only things that I'm going to be able to cancel are the electrons. Sometimes there's other things you can cancel as well, but in this case, only the electrons. So now step 7, I'm going to go ahead and add the two half equations together and cancel out those electrons. And here I am with my overall equation. And if I'm smart and I've got time, I'll go through and I'll make sure that everything balances on both sides, including the charge. So I've got 5 ions on the left and I've got 5 ions on the right, so they are good. I've got 8 hydrogens on the left and I've got 4 times 2, 8 hydrogens on the right, so they are okay. I have 1 manganese on the left and I have 1 manganese on the right, so they are okay. I've got 4 oxygens on the left, and then I've got 4 times 1, 4 oxygens on the right, so they are okay. Now the charge is going to get a little gnarly, and it's going to take a little more effort to add all of this up without error, but it really is the key thing to making sure you've got this right. 5 times 2 gives me 10 plus. Then I've got another 8 plus there, so that's 18 plus. and then I've got to take 1 away, so that's going to give me 17 plus. What about on the right hand side? 5 times 3 plus is 15, and then 2 plus there, so that gives me 17 plus. So there's very little doubt that this guy is balanced, right? Okay, so that's it. Now, what is step 8? Step 8 begins with if basic conditions. It said that this was acidic condition, so we don't have to worry about step 8. We're done. Okay, we're done at this point. So just one last thing, again, as I said, always check your equation for your balances for both atom type and also total charge. Okay, so you're done. So that was quite a complex one. We used pretty much all of the rules except for step 8. So there's only one thing left to do. That's the big kids problem, is where we use all 8 rules, including that final step. So it's just going to be just like what we did for acidic solution, but we're doing that one final step 8, and that step 8, it's a doozy. So here's our problem. Mn2 plus O2 gives MnO2. Whew. Alrighty, so doesn't look too bad, and then it says basic conditions, and you're kind of like, ugh, that is kind of awful. All right, so some people, they'd be like, well, this already balances, right? 1 manganese, 2 oxygens, 1 manganese, 2 oxygens. But you'd be totally wrong, because the total charge on the left is +2, and the total charge on the right is 0. So don't be fooled into thinking that it's already balanced. It's not balanced if the charges are not the same on both sides. So we're going to break this into 2 half reactions. So we've got Mn2 plus and O2 as our reactants, right? So we need our equations are going to begin with that. There's a little bit of a problem though. It's kind of obvious that Mn2 plus has to get converted to MnO2, but there's only one product. So the thing to keep in mind is that when you have a half equation that begins with O2, you don't have to specify a product. And if you think about the steps, you'll understand why this is. It's going to work out anyway because we always balance oxygen by adding water. Okay, so don't worry about specifying a product for your half reaction that starts with oxygen. Okay, so what do we do now? We balance atoms except oxygen and hydrogen. Well, we got 1 manganese, so that's already balanced. So that was real easy doing step 2. Then step 3 is balance for oxygen by adding water. And you can see that we have 2 times oxygen on our top one here, and we also have 2 times oxygen here. So we're going to need 2 waters on the left-hand side there, and we're going to need 2 waters on the right-hand side in our reduction. So we have to balance for oxygen by adding water. So just like I said, we need 2 waters on the left to balance for the 2 oxygens on the right, and in our reduction, we need 2 waters on the right to balance for our 2 oxygens on the left. And now we feel a bit more comfortable because both our reduction and our oxidation has a product specified. Sometimes it's a little bit like you feel a little awkward when you don't have a product specified for your O2 reaction. So our next step, what was it? Balance for hydrogen by adding H+. And if you look here, I got 4 hydrogens on the left in this guy, so I'm going to have to add 4H plus over here, and then I've got 4 hydrogens on the right here, so I'm going to have to add 4H plus on the left. So balance for hydrogen by adding H plus, I need 4 on the right and 4 on the left. So now all of my atom types balance, right? All of my non-oxygen hydrogen atoms balance, my oxygens balance, my hydrogens balance. I've got all of that figured out. What doesn't balance at this point is the charge. And how I'm going to balance the charge is by adding electrons to the more positive side of our half reaction. So the total charge on my oxidation is +2, and the total charge on the right-hand side of my oxidation is +4. So always add it to the more positive side, so I'm going to have to add in 2 minuses. In this case, the total charge on the left-hand side of my reduction is +4, and the total charge on the right-hand side of my reduction is 0. Again, always add to the more positive side, so I'm going to have to add in 4 minuses on the left. So step 5, balance the charge by adding electrons to the more positive side. So added my electrons in, I need 2 electrons on the right hand side to be added to my oxidation half reaction, and 4 electrons to be added to the left hand side of my reduction reaction. These electrons should always end up on opposite sides of the arrow. For the oxidation, electrons should be a product because electrons are being lost. For the reduction, the electrons should be a reactant because the electrons are being gained. Okay, step 6, multiply one or both of your half equations by a whole number so that the number of electrons lost equals the number of electrons gained. And you can probably see what I'm going to have to do is multiply my oxidation half reaction by 2. So everything in there gets multiplied by 2. So that's what I've done here. That got multiplied by 2, 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 and that got multiplied by 2. So now the number of electrons lost equals the number of electrons gained, and I'm ready to add these guys together. I'm going to add them together, cancelling wherever possible. Now, in this case, I can cancel a lot more than just the oxygen, than just the electrons. You can see that I can also cancel some water, and I'm going to be able to cancel some hydrogen ions. So let's have a look at what that looks like. So step 7 is cancel the 2 half equations together, and you can add the 2 half equations together, cancelling wherever possible. And so the first thing is that the electrons, you always want to make sure that they can cancel. They can. And then I can get rid of 2 of the waters, leaving just 2 remaining. And then I can get rid of 4 of the hydrogens, leaving 4 remaining on the right hand side. So when I do all of that, and I have to be a little bit careful to keep track of everything, I've got 2Mn2 plus 2H2O plus O2 gives 2MnO2 and 4H plus. And everything looks like it's balanced. I've got 2 manganeses, I've got 4 hydrogens, I've got 4 oxygens. It looks great. The only problem is that this is in acidic conditions. This has acid present, it has H plus present, and our equation clearly is labeled as being under basic conditions. So I have to convert to basic conditions. And for the first time, I'm going to be using step 8. And step 8 says that what I'm going to do is I'm going to add 1 OH minus to both sides of the equation for every H plus that is present. So in this case, I've got to add 4 hydroxide ions to either side of the equation. But then I've got to go one step further. I have to recognize that hydroxide ions and hydrogen ions combine to make water. So anytime I have hydroxide ions and hydrogen ions on the same side of the equation, I'm going to combine those to make water. And then what I'm going to do is I'm going to cancel further, if I can, any water molecules. So let's have a look and see what that looks like. So I can see here I need to add 4 hydroxide ions to both the left-hand side and the right-hand side of my equation. So 4 hydroxides, and then I added in 4 hydroxides. Now I've got to combine hydroxide and hydrogen ion to form water. So I did that and I formed 4 waters. And then I have to cancel wherever possible. And what you can see that I can do is 2 of these waters I can cancel out, and then that leaves 2 remaining. So here's my overall balanced equation, and it's in basic conditions, right? There's the presence of the hydroxide ion. So 4 hydroxides plus 2Mn2 plus O2 gives 2 MnO2 and 2 waters. And nothing repeats on either side of the arrow. There's no electrons left over. And if I added everything up, if I add up the numbers of each atom, let's just do that. Oxygen, hydrogen, manganese, and of course, charge. What do I get? 4 plus 2, 6 oxygens on the left. 2 times 2, that's 4, plus another 2, 6 oxygens on the right. So oxygens looks good. 4 times 1, 4 hydrogens on the left. 2 times 2, 4 hydrogens on the right. 2 manganeses on the left. 2 manganeses on the right. Looking good. So all of my atoms balance. What about my charge? I got 4 minus there on the left, and then 2 times 2 plus, I got 4 plus. So total charge on the left is 0. On the right hand side, there's nothing there that's got a charge, so that's also 0. So I finally got there. After my 8 steps, I was able to determine the balanced equation, all right, under basic conditions. So that's awesome. Okay, so we looked at oxidation and reduction reactions. We defined the terms oxidation and reduction, oxidizing agent and reducing agent. We established the concept of oxidation number and how it allows us to identify what is being oxidized, what is being reduced, what is the oxidizing agent, and what is the reducing agent. We then went on and developed an 8-step method for balancing redox equations under any of the common conditions we might encounter. Conditions where it's acidic, conditions where it's basic. So it's quite complicated and you will need to practice, and for that reason I posted a bunch of worksheets online and I'd highly recommend that you have a look at those. Okay, good luck with everything.